Hi there, my name is Sean from Primus Labs. Today, I'm going to show you a solution about verifiable and privacy-preserving proof of reserve solution for ETH protocol. So we provide this solution for partners, Unitas. So Unitas is a high ETH protocol that can provide APY up to 50%. They also have a stable coin. So all the stable coin is backed by assets they have off chain and on chain. So in this transparency page, they show that they have like enough assets in their account, and these kind of assets consists of two parts. This part is the on-chain assets. So you can actually check all the addresses about their balances to make sure that, okay, this number is actually correct. And the other part is from centralized exchanges, like off-chain. So the problem we're going to solve that we want to make sure that this kind of number is trustless, or it can be trusted, or um, can be verifiable. So you don't need to trust the number here. They put it on here, or you can like use general proof systems to verify that, okay, this is actually from Binance and the number is actually correct. So there is kind of a very, very simple thing to do that. Unitas can just public all their like read-only API keys to public, and then everyone there can verify that by accessing the APIs using these API keys. Yeah, they can make sure that this number is correct. But the thing is that Unitas also lists all these informations about strategy, positions in different accounts, and all the details, all the actions they are now they have done or going to do. So they don't want to leak that private information. So what we have provided is that we can guarantee two things. First of all, this data is actually from Binance. Then, Unitas does not need to reveal anything else, including like positions, like strategies. They only need to reveal the total numbers. This is another property called privacy preserving property. So how we do that? And we propose this DVC mode using zkTLS and zkFH. So DVC means that data verification and computation. So it means that we kind of using zkTLS to prove the authenticity of the data. And then we use zkVM to prove the computation of this private data. Here, the DVC client is a script that show you how to access to our zkTLS network on base, and also how to connect with zkVM. And in this zkVM DVC program here, so it has a application program. That means you need to first verify that the data from the client is actually attested, and then you can do your customized checks, computations like aggregations, like filter, like um, um, all the other things you want to put it into the business program. So we're now using Succinct and using their like private pre network to do that. And so the final result is a proof, is a zk proof that anyone can verify that the total amount is correct, is from Binance, and you don't need to anything else about all the strategy details. So let's go to the code. Yeah, we already have downloaded the DVC client. Let's see what we have in that file. Oh, you can see everything. So yeah, all right. for now, I already set everything here in the .evn file, so including my private key, and I'm accessing to the main basenet and the API keys here. So let's kind of run the code here, demo, Binance. Yeah, it's working. So nice. So yeah, here's a few things I want to break down. So for now, we kind of like initiated the private network. So it means that the client can initiate a transaction to the base network, and then they actually submit this task to the network, and the network or smart contract can select one of the testers randomly. And in this case, the client and the tester, they are running the zkTLS protocol here. So a few things I want to point out is that for now we are running this MPC-TLS protocol because the Binance have a very restricted IP restriction. So all the connections of this API key has to be from this exact IP. So we need to like using MPC-TLS. And the other part is that all the data in the attestation is actually hashed. So we add these operations hash to make, because the attestation in our network is public. So we don't want to leak these prem messages to the base chain. So everything is hashed to make sure that there is no leak of the private information. So we also have these attesters, signatures, and the URL. Yeah, I want to mention that all the attesters in our zkTLS network is run inside DTE using the stack. And so we're now kind of using Fala. Yeah. After that, the client will verify the result. This is the verification of the attestation, so it's not very important. And finally, we put everything to Succinct private proven network. So yeah, we have got the result here. So they prove all the like programs we write in Rust. Yeah, so this is actually the proof and the proof ID. Let's copy this proof ID and go to their Succinct Explorer so we can check that. Yes, it's coming out. Oh, yeah. So yeah, it takes like 52 seconds. And the total cycle is about 1.8 million cycles. And here is all the proof you can get from this link. And this is the program we deployed in the network. Yeah, and I think the latest one is our proof right now. Our proof before. So yeah, we can you can so anybody can check that this proof is actually like you can verify using these proof systems and the verification keys. So make sure that everything is verifiable. So yeah, that's the whole process of our DVC mode. Hope you enjoy.